Why there's more matter than antimatter floating around. Imagine the Big Bang, the colossal explosion that gave birth to our universe. Now, you might think that it would have created equal amounts of matter and antimatter. But here's the kicker, this didn't happen. Instead, we ended up with a universe dominated by matter. So where did all the antimatter go? To tackle this, let's first understand what baryons and antibaryons are. Baryons are particles like protons and neutrons that make up the matter we interact with every day. Antibaryons are their evil twins, same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of energy, producing gamma rays. Now, both the standard model of particle physics and Einstein's general relativity can't explain why there's this imbalance. According to these theories, there should have been equal amounts of matter and antimatter, yet here we are, living in a universe full of matter. One popular theory involves something called baryogenesis. This theory suggests that during the early moments after the Big Bang, certain physical laws might have acted differently for matter and antimatter. Perhaps some interactions favored matter just a tiny bit more, leading to an excess of baryons. Another intriguing hypothesis proposes that matter and antimatter ended up in separate regions of the universe. We might have antimatter galaxies out there, but they're so far away that we haven't detected them. If these regions existed, we would expect to see gamma radiation at the boundaries where matter and antimatter meet. However, after decades of searching, no such boundaries have been found, so it's becoming more unlikely that this is the answer. Despite all this brain power and fancy theories, we still don't have a definitive explanation for baryon asymmetry. It remains one of the great unsolved puzzles in physics. But don't let that discourage you. Science is all about asking questions and seeking answers. Even if those answers are elusive, who knows, maybe one of you will be the one to crack the code. What if I told you there's another mind-bending theory that could potentially explain this cosmic conundrum? Enter the concept of the mirror-anti-universe. Imagine the Big Bang not as a singular event, but as a double-sided explosion. This isn't just science fiction. It's a theory proposed by physicists from the Perimeter Institute for Theoretical Physics in Canada. According to this model, the state of our universe doesn't violate the CPT symmetry, charge parity and time, because the Big Bang could be considered as creating a universe-anti-universe pair. In simpler terms, our universe, rich in matter, has a counterpart, the anti-universe dominated by antimatter. This anti-universe flows backward in time from the Big Bang, expanding as it does so, just like our universe expands forward in time. Its spatial properties are inverted compared to ours, akin to creating electron-positron pairs in a vacuum. But how does this explain baryon asymmetry? Well, this model suggests that temperature fluctuations in the cosmic microwave background, or CMB, are due to the quantum mechanical nature of space-time near the Big Bang singularity. Essentially, a point in our universe's future and a point in the distant past of the anti-universe serve as fixed classical points. All possible quantum-based permutations exist in between, creating a complex yet fascinating picture. Quantum uncertainty ensures that our universe and the anti-universe aren't exact mirror images of each other. This discrepancy could explain why we observe more matter than antimatter. However, this model hasn't yet shown if it can reproduce certain observations about the inflation scenario, such as the uniformity of the cosmos on large scales. But wait, there's more. This theory also provides a natural and straightforward explanation for dark matter. The universe-anti-universe pair would produce large numbers of super-heavy neutrinos, also known as sterile neutrinos. These elusive particles might even be the source of recently observed bursts of high-energy cosmic rays. So, while the mirror-anti-universe theory is still in its infancy and needs more evidence to be fully accepted, it offers an intriguing perspective on some of the most puzzling questions in cosmology. Now let's dive deeper into a pivotal cornerstone of modern cosmology: the Sakharov Conditions. In 1967, Andrei Sakharov proposed a set of 3 necessary conditions for a baryon-generating interaction to produce matter and antimatter at different rates. These conditions were influenced by the recent discoveries of the cosmic microwave background and CP violation in the neutral kaon system. The three Sakharov conditions are: 1. C-symmetry violation ensures that interactions producing more baryons than antibaryons are not counterbalanced by the opposite. CP symmetry violation prevents equal production of left-handed baryons and right-handed antibaryons and vice versa. Interactions must be out of thermal equilibrium to avoid CPT symmetry, ensuring compensation between processes, increasing and decreasing the baryon number. Currently, there is no experimental evidence of particle interactions breaking baryon number conservation perturbatively, which suggests that all observed reactions conserve baryon number. 1. In the standard model, CP violation appears in the quark mixing matrix of weak interactions and possibly in the neutrino mixing matrix. The first CP violation was confirmed in the 1964 Fitch-Cronin experiment with neutral kaons. Despite CP violation in the standard model, it is insufficient to explain the observed baryon asymmetry of the universe, indicating the need for beyond standard model sources. The LHCb collaboration found a potential new source of CP violation in the decay of bottom lambda particles, showing a significant asymmetry. Searching for electric dipole moments of particles is another method to find additional CP violation, as their existence would imply T-symmetry violation. 1. This rapid expansion prevents particles and their corresponding antiparticles from achieving thermal equilibrium, reducing pair annihilation occurrences. These conditions are critical for understanding baryogenesis and the observed matter-antimatter asymmetry in the universe. While Sakharov's conditions provide a theoretical framework, the quest for experimental evidence continues.